All right, so this is what we covered on Monday. It's sort of an embellishment day and maybe a look back day on some of the things that we did in chapter 1 that maybe we can do a little easier. So you may recall on the day where we were making box plots and finding outliers and modifying box plots and all of that. You remember that we did this example number 2, weight in pounds of 20 randomly selected juniors at Cinco Ranch. We got our 5-number summary. We went ahead and modified the upper and the lower end to check for outliers. So 1.5 times the IQR added to Q3, 173. That made 179 an outlier. And then we checked the bottom side and had no outliers. You remember this. So then we pulled into the next biggest value on the right side, the 169, which is this right here, and we exposed that outlier and then used the rest of the 5-number summary to build the graph, and the rest is history. Well, you still need to be able to do the 1.5 times the IQR thing. Even if you only get like a 5-number summary, then you could check for this being an outlier, the 179, or you can check for the 121 being an outlier, or both. But you can't really identify any other outliers because if you only have the 5-number summary, you just don't have the rest of the data. So you still need to be able to at least figure out whether the minimum or the maximum is an outlier in a 5-number summary. So you need this formula. But if you have the full data set, well, you've got some leeway insofar as graphing goes, because, well, here is your n-spire with those same weight values put in here, those 20, and I am going to look at some graphical options for us. So the first one I'm going to show you, whoops, we don't need that. We do need to go to a graph, stats graph, which is that. And nothing much to see here until we add the variable, and there's the dot plot. And maybe this is an outlier and maybe these two are, we don't know, but that's a dot plot. Well, you have other options that I didn't show you. If you go to plot type under menu, you can do a box plot, and it defaults to a modified box plot. In fact, I don't think you have any other option on the n-spire calculator. And what it does is it shows you the outlier. So if you mouse over it, you can see what it is. And if you have another one, you can mouse over it too. All right, here's your modified maximum. Remember, we had to pull it in from here. And Q3, it even tells you that, median, Q1, minimum. So very nice. The other option that we can do is to do a histogram. And so that's the histogram it's going to make for us. Now there are 20 data values, so there should be 4 bins. And we have a lot more than 4 bins here, but we can still see that it's skewed to the right. We can still figure out that maybe that's an outlier, maybe these two are. We can always check with a box plot. We could probably go in and find a way to modify this to extend these bin ranges and make them a little wider so that we can have fewer of them, but we're not constructing these things anymore. I mean, if you need a histogram for a quickie look-see, then you can just pop this up. But the main thing that you might want is the modified box plot, so you can identify the outliers, right? And don't forget, box plots don't show shape. We can do the same thing on your TI-84, albeit maybe not quite as cute and clever. So let me get rid of these things so that this is kind of by itself, and I have the data in here in L1. Same thing. So I'm going to quit out of here. Then I'm going to do second and stat plot, and you got 3 different choices for plots. You can actually plot more than one box plot in the same graph, for example. I'm going to go to the first plot, so enter, and you got to make sure it's turned on. Mine was, but it's not really automatically that way. If you don't turn it on, it just won't work. So let's go down. You've got a number of different graphs. This one here that's blinking is a modified box plot, because if you look in between the blinks, I'll move off it, it's got dots sticking there. So those are outliers. So if you have any, it's going to show them. The one next to it is a non-modified box plot. It will not show outliers. This is the one all the way to the end is a scatter plot. We'll need that eventually. And that's a histogram. So let's go ahead and choose the modified box plot. Everything looks good. You can make the marks, your outliers, little squares or little pluses or a little dot, whatever. All right, but let's go ahead and hit graph. And I don't see the whole thing. The scaling may be off. What you need to do is to zoom 9, which is zoom stat. You're going to use that a lot. And now everything shows. And it shows the outlier. I don't know why you would want to do one that's not modified, but you can if you want. And if you go and hit trace, you can see your minimum, Q1, median, Q3, modified maximum, and absolute maximum, which is your outlier. This will do a histogram, as I think you saw. So I'll show you that. And we may get an error, which is not too uncommon. And let's graph that. Oh, okay. Sometimes if you get an error, you need to zoom 9 before you do this. And you can see that there's far fewer bins, but it is skewed to the right. It's just not revealing the outlier here. So like I said, these histograms on these graphs are okay, but they may not fit the bill for everything. So, but they're there. All right. So one other thing I wanted to show you on the calculator, but before I show it to you, I want to go, if I can find it, to this. So we had done these notes the other day. Remember modeling low birth weight babies, and the babies are born with a mean of 3,250 grams for weight and a standard deviation of 550. We did a left tail calculation. We did a right tail calculation, and then we did one that was kind of somewhere like in between with no infinity as a part of it. So this one, we started out just by, P, we just did X rather, X to Z, and finally we got to P. And we went through it by standardizing, getting the Z scores, and doing a normal CDF. Well, I still want you to do this step right here. And I still want you to show this step right here. But getting these actual Z-scores is kind of optional. If you draw the curve and do those two things, you're pretty much good to go. So what I didn't show you, and it works in both calculators, is let's go home and just open up a Scratchpad. Is that you don't have to necessarily standardize. So if I start to do a normal CDF, for example, so it's menu 5 and normal CDF. All right, my lower bound in that problem was, I think, negative 0.45, but I'm just going to go ahead and put the original value, 3,000, in the original metric of grams. And then the upper bound was 4,000. All right? Now, if I am not going to standardize, it means I'm in the original normal curve, but not in the standard normal curve. So I need to change mu and sigma. So mu was 3,250, and your standard deviation was 550. And you should be able to get the exact same probability that we got when we standardized. And remember, 0.5889? Well, you know what? It may be a little different from what you got because this is not rounded anywhere. So I think it was 5.678 or something like that. But again, we're dealing with just minor fluctuations at these lower extremes for the decimal places. And that really doesn't matter because it's all an approximation anyway. But see, no 0 and no 1 and no z-scores. It converts to z-scores within automatically. So you're welcome to do that if you want, but just show me all the steps leading up to it. Okay, so that brings me to the third thing I wanted to show you, and this is something that you can pick up in the reprints, and I hopefully will put that in the announcement for today. And I just want to go ahead and look at some percentiles when we're dealing with normal curves. So Helen recently took the SAT math test, and the scores for it is normally distributed with mean of 500 and standard deviation of 100. So we can just go ahead and make the shorthand notation. Mean of 500, standard deviation of 100. Okay, there's your complete description. So if Helen scores somewhere within the distributions I, Q, R, what range of values will Helen's SAT math score fall within? Okay, IQR is 25th percentile and 75th percentile and blah, blah, blah. So I'm just going to start out with some kind of a generic question that I'll add on to this one, and it'll just be, what is the 40th percentile? Just so that you can see kind of a generic kind of question about percentiles. So a percentile, remember, is a value below which that number, like 50th percentile, 50% below and 50% above. So I'm going to, so here would be the center, and off here would be like the cut for 0.4, and on the other side would be 0.60. And what we need here is the z-score, because we're going to do x minus mu over sigma equals z. So we need this z-score at this cut point. So that'll be inverse norm. And remember, inverse norm reads left to right, and it's set up exactly the way we want it. So inverse norm 0.40, and that will give you the z-score of, let's see, negative 0.2533. Negative 0.2533. A lot of times when I am solving for x, I will go a little bit beyond 2 decimal places for z in order to get a little more accuracy. So don't freak out about my rounding. I mean, anything 2 or more is fine, but if you want a little extra detail, go to 4. So what we want is, let's see, x is going to be the value we're looking for, minus 500, that's your mean, over 100. And I'm going to use equal because this is not really a range of numbers, it's more of a point estimate. Negative 0.2533. And then you just multiply each side by 100 and add 500, and you get x equals 474.6653. And I'm just going to put in SAT math units, just so you know that units usually accompany this. All right. Now I know that SAT scores are to the nearest whole number. If you want to round this to like 475, that's fine. Okay. But I'm just going to leave it just like this for the accuracy. And so that gives you a sense for how we're going to do percentiles. So if we want the IQR, we're going to have to get Q1 and Q3. So second question, I'm going to start addressing this one up here. What is Q3? And remember, Q3 is your 75th percentile. And so we're going to set this up exactly the way we did with the 40th percentile. Let me scoot this up a little bit. And it's just going to be a different cut in the normal curve. So here's the normal curve, and let's go ahead and put the 0.75 cut point up there. So 75% below, and so that would be 0.25 above. So we want inverse norm, so we can get this z-score. So inverse norm 0.75, and this will give you 0.6745, and that'll be this z-score here. This is a number that comes up all the time. In standard normal calculations, this is the value for Q3. All right. So remember it. You don't have to always do the inverse norm to remember these things. Just this comes up a lot, so put it in your memory. So we'll figure out the Q3 value in regular units. So x minus 500 over 100 equals 0.6745. And multiply by 100 and add 500, and you're going to get x equals 567.4490. And that's in SAT units. All right. And again, this can be rounded down to 567, but let's maintain the accuracy. So we're going to need Q1. Well, Q1 is your 25th percentile. So let me just change colors here. And we're talking about, this is just going to be down on the other side, right? And it's going to be the same number as this, except it'll just be negative. So that's the z-score for it. So what is Q1? All right, all we have to do is x minus 500 over 100 equals negative 0.6745. Right, looks like I wrote the wrong thing here. That should be a 4. All right, and yeah, see, they're the exact same number, except one's on the left of 0 and the other's on the right. So here, x is going to equal, when you multiply by 100 and add 500, 432.5510. And again, that's in SAT units. All right, and so if we want to answer the actual question, that's just going to be, IQR is Q3 minus Q1. So that'll be your 567.4490 minus 432.5510, and you'll get your answer, 134.898. And that will also be in SAT units. So yeah, this is actually a pretty quick process. I mean, we really don't need to do number 1. That was just, okay, how do we get any percentile? All we really needed was to get Q3, and so you can just figure out Q1, or let's say or Q3 by doing x minus mu over sigma equals plus or minus 0.6745. And it's as easy as that. But then you got to get the numbers and subtract them and all that. So I've got one more thing to show you. So I'm going to pause before I go to show you that. So hang on. All right, so the last thing I wanted to look at was this catapult problem. And I assigned it a long time ago. And it's just hard to get the time to go over these things. I know that I oftentimes dismiss you early, and that would be a good time, but it just seems like it's a necessary thing, sort of. So anyway, at least we're getting to it now. And you recall the problem. 2 parents, they've built a toy catapult for use in a game at an elementary school fair. To play the game, students will attempt to launch ping pong balls from the catapults so the ball lands within a 5-centimeter band. All right, this is the 5-centimeter band, and that's in gray. Target line will be drawn through the middle of the band, so this is if you hit it kind of perfectly. As shown in the figure, all points on the target line are equidistant from the launching location. So this is like a sector of a circle, and here's your center, and these are all radii. You get the idea. So you get a little margin of error. If the ball lands within the shaded band, the student will win a prize. So the parents have constructed 2 catapults that are a little different. So they're probably not going to, function the same. They want to test these catapults before building additional ones. So under identical conditions, parents launch 40 ping pong balls from each catapult, 80 total, and measure the distance that the ball travels before landing. Distances to the nearest centimeter are graphed in dot plots. See, I told you we don't use them much, but AP loves them. They use them a lot. And so here are the two dot plots. And the first question is, comment on any similarities and any differences in the two distributions of distances traveled by the balls launched from Catapult A and Catapult B. Okay, this is not one of the longer questions on the AP exam. It's more like a 13-minute variety. So there's only so much you can do as far as, figuring out a lot here. Let's see how they scored it, and you can see that they kind of went ahead and got sort of compact in their explanation. So for part A, both distributions are roughly symmetric in mound shape. They were. The center of the distance is for Catapult A, and they did the median because you can count it. It's like the average of your 20th and 21st shot. It's slightly lower than the center of the distances for Catapult B. There is more variability in the distances traveled by the ping pong balls launched with Catapult A. You see they did not quantify that. There are distances that are extreme enough to be called potential outliers in Catapult A distribution, but there are no outliers among the ones in Catapult B. So since you don't have really a whole lot of time to get a 5-number summary and do your 1.5 times the IQR, they're letting it go with you just mentioning them without having to quantify them. Of course, if you do quantify and find that they're outliers, then they'll accept it. But, they're just giving you an out to say as little as you need to and get on with the rest of your test. So there's that question answered according to them, and we can see the scoring guideline in a minute. Oh, let's go now, let's just keep them together. So part A is essentially correct. I'm down here. If the student correctly identifies similarities and difference in center, spread, and shape. And you notice that they didn't talk about outliers, all right? So part A is essentially correct if the student identifies those three for the two distributions. It's partially correct if you identify similarities and differences in two of the three, and it's incorrect for anything less. All right, correct comments regarding outliers should be viewed as positive. However, comments about outliers do not count as one of the three required characteristics. Interesting. All right, if the parents want to maximize the probability of having the ping pong balls land within the band, which one of the two catapults, A or B, would be better to use than the other? Justify your choice. Okay, this will be interesting when I read it to you. Catapult B would be best because the distances vary less, we've already said that, about the center of the distribution for Catapult B. If Catapult B is properly placed, the balls launched will have a higher probability of landing in the narrow 5-centimeter wide target band. All right, that makes a lot of sense to me. So using the catapult that you chose in part B, hopefully it's A, how many centimeters from the target line should this catapult be placed? And you've got to explain it. Okay, here's where people will miss points. All right, the catapult A should be placed 138 centimeters from the target line. Since the distribution of distances for catapult B seems fairly symmetric and mound-shaped, the median is a good representation. See, it's the same as the mean of the center of the distribution. So placing catapult B at this location, 138 centimeters away, would have resulted in a high proportion. Now they did count it out. 30 out of 40, or 75% of the ping pong balls from this sample of launches would land in the target band. Interesting. Okay? So they did ask you to quantify this right here, the 0.75 value. Okay. So part B is essentially correct if catapult B is chosen using a rationale based on variability. It's partially correct if catapult B is chosen, but the explanation does not refer to the variability. And it's incorrect if part B is chosen with no explanation. See why I was so grumpy about you explaining things on your first quiz? All right, and part C is essentially correct if it's placed at the median or the mean. If you want to go ahead and assign values to each of the shots and get the mean, it'll eat up a lot of time, but you can do it. So the median or the mean of the distances, and the explanation addresses why the median or mean was selected based on a property of the chosen statistic that relates to the context of the problem, or the catapult is at a distance that gives a range of numbers, and the explanation indicates that the chosen distance results in a high proportion of balls in the sample landing in the target line. So part C is partially correct if it's placed in an acceptable distance, but the explanation is incomplete or incorrect, and it's incorrect if you're less than 137.5 or more than 139.5 centimeters from the mean. So note, simply saying because it's the mean or median is incomplete. Some students may confuse the 5 centimeter band as meaning 5 centimeters on either side of the target line. So in other words, it's 10 for that band instead of 5. Like it's 2.5 above, 2.5 below, not 5 above and 5 below. If the student chooses the mean or median and satisfactorily addresses why was selected, or a value of 137 to 140, and the explanation indicates the chosen distance results in a high proportion of balls, blah, 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 you'll get a partial for that. Student gives the distance from the catapult to the front or back of the shaded band rather than the distance to the target line, but it otherwise is correct, you get a partial. If the student picks catapult A in part B and follows through correctly in part C, then part C should be scored essentially correct. Okay, so there's your scoring for it, which you're welcome to pause and look at. That's all I've got for you. So I'm going to go ahead and sign off, get rid of this, and we'll see you tomorrow for your quiz.